Hi everyone. So let's start the lecture. So it's robotics and mechatronics, and we first take robotics for probably major part of the semester, and then probably last few weeks we will take up with mechatronics because the content, if you look at robotics and mechatronics, is too much for one semester. But there are certain things that we have not covered in previous semesters under control systems that we take the as mechatronics part here, leaving most of the semester for robotics. Right. Course details. This is 60/40 module. Written exam will get you maximum 40, and continuous assessments throughout the semester will add up to about 40% of the final assessment. The contents, we will look at robotics, the big picture, what is robotics and why it is important, different types of robots, applications, what the world is like with robotics and most of the related technologies, right? World would have been very different if not for robotics today, right? And we want to look at robot manipulators in particular in great detail, because manipulators is actually the core of robotics, right? And also the controls, a bit of controls. You have done a lot of controls in past 2 semesters. We look at a bit more into that here as well. Because when it comes to robotics, you have to control position, right? You know that. Sometimes velocity also, acceleration, right? And also when you are handling objects, you need to look at the forces you are applying, the robot is applying on the outer world, right? Think about a very unique application, robot surgery, right? There, the robot is not handling material, but robot is in contact with human body, right? Very delicate organs within the body of a human. You have to make sure that under no circumstances the robot applies more than safe force, right? Contact force. So it's extremely important in such applications, and to a certain degree in all other applications, that to control the contact force, right? Together with the position. And also obstacle avoidance is another area. If you look at autonomous vehicles, um, and even the manipulators in industries where they have to operate in cluttered environments to avoid obstacles, right? So that is about the content of the module. And then MATLAB based assignments are there in right throughout the semester. I'm sure you are pretty good in robotics now, MATLAB now, spending some time in MATLAB in early semesters, right? So here also you use MATLAB, but with a special add-on to it, Robotics Toolbox. So now it's up to you to go to the internet, look at the robotics toolbox, right? If you just drop into robotics vision and control, right? I will write it in the chat box. Robotics vision and control by Peter Koch. Um, right. So just look at the chat box. Robotics, Vision and Control. That is the book by Peter Koch. I think he's now at Australian National University. Go to the website, right? You can see the robotics toolbox there. Download, and if necessary, unpack it and then link it up from from MATLAB. In the MATLAB, you go to the MATLAB. I think I explained you how you can develop your MATLAB installation. You can have toolboxes because MATLAB is entirely a set of toolboxes, right, connected together. So whenever you have a toolbox, you have to tell MATLAB where the toolbox is. Okay, so that is what you do using what is called a set path, right? All these things we discussed in early semesters. So download robotics toolbox and set path from MATLAB to the robotics toolbox, right? Then you can enjoy all the commands, robotics related commands within MATLAB. And then uh, we want to do robot control exercises to deal or engage with actual manipulator. We have a manipulator, but there's a little problem. The manipulator battery has drained for quite some time now. During COVID period, we couldn't replace it. A lot of problems. So therefore, at the moment, the manipulator is not in operational condition. We need to fix it. After that, if you're able to do that under the present circumstances, we can't purchase anything from overseas. Even the battery is required for the manipulator. Even if you replace the batteries, I don't know whether the calibration is still there. If not, we have to recalibrate it. Recalibration can be done with an expert from the manufacturer side in Canada online. But if it fails, we have to send a robot back to Canada or maybe in India, the agent to recalibrate and bring it back. So a lot of work to be done. Therefore, I'm not very hopeful about actual hands-on experiments within this semester. But assignment-based ones we will do using the same robot manipulator, right? Simulation and trajectory planning. Okay. By the way, do you hear me well?
Yes, sir.
Okay.
Yes, sir.
So, fine. Am I loud enough? How is now? I'm increasing volume now.
Fine, sir. We can hear you.
Right. Excellent. So let's talk about history of robotics a bit because it's extremely important to know the history of robotics. When you study a new subject, new area, it's always important to know bit of history, right? Bit of history, the evolution, how things happen as a story. Then you remember it very well and you become very mature in that subject. I have seen people who have studied various disciplines, but only up to date things, not the history, not how it came about in the first place. And certainly you can see something missing in those people, right? They always know uh, what they use today and the latest things, but they don't know how those modern things are connected to the recent history or the past. So therefore, it's not very beautiful knowledge in a way, right? It's very crude knowledge, very rigid knowledge. There's no beauty in that knowledge. So if you want to make whatever knowledge, something beautiful, something very nice, something you can talk about and enjoy rather than solving sums or coding in a computer. You need to look at the history. You need to look at the history. Every time you try to learn about history of any modern science or any modern technology, you beginning to like it. You feel like passing through entire history, different people, developing certain things, and now we are here today. So that's why it's very important to spend some time, little time, to look at how that subject, as we see it today, actually came, right, from many, many decades ago. Now, if you look at the definition of robot, actually, robot is not an English word. It's a Czech word, right? And then adapted to the English language. The definition of a robot is a piece of machinery that could perform tasks which are generally ascribed to humans, right? You know the tasks generally ascribed to humans. As humans, we do a lot of things, right? Various activities. But if you look at some of these activities where intelligent decision making is required, we are referring to those activities. What about now? I'm speaking to you now, right? I think what to speak. I line up the words and I create the sentences and then I speak. Okay. So this is a very high level cognitive action performed by humans. Other animals, nobody can do that, right? So that is something ascribed to humans. And think about I can stand up from here and walk to the road, and there are so many obstacles in the way. I can avoid them. I can take turns, and I can walk without toppling down, right? So that is a very skillful thing, right? And only humans can do that, right? Or some animals also can do that. Okay. Uh, so that is again something very cognitive. So what about face recognition? I can recognize my kids, my mother, my wife, my friends, the leaders of different countries, right? Famous faces, right? So how do I do that? We still don't know, but that is something only intelligent beings like humans can perform, right? So if you see a machine, which is not a human, okay, machine performing some of these things, recognizing voice. When my mother calls my name, I know this is my mother calling me, right? When a friend of mine calls me, I know that's his voice, right? Identify different sounds and voices, right? Things like that. If you see a machine performing some of these things, right? Some advanced activities that are generally ascribed to humans, most probably that machine is a robot, right? That is how we define a robot. It's not a very hard definition, but it conveys you how to differentiate a robot from other machines. You know, there are so many other machines, right? Like bread toaster, it's not a robot. A washing machine is not a robot. And then typewriter is not a robot. A car is not a robot. Airplane is not a robot. And what is a robot? A robot is a machine that performs some activities which are generally ascribed to humans. Now, with modern technologies, it is becoming increasingly difficult to differentiate a robot from a non-robot machine. Say, for example, a car. We know the old cars and most of the present cars are not robots. But there are some cars which are performing some functions which are generally ascribed to humans. In that case, these cars can be identified as robotic cars. Robotic cars. Okay. So you can draw the line, right? A hazy line, a fuzzy line between non-robots and robots if you apply this definition case by case. Okay. And always there's a room for error. There's a gray area where you can only argue, right? Someone say this is not a robot, and someone say no, no, this is robot. So This happens when that machine falls right in between. Okay. So the word first appeared in 1921 in a stage play by Karl Capek. Uh, uh, and in his stage play drama, right, there was a character like this, RUR, Rossum's Universal Robot. So this is the first time the world heard about the word robot, RUR, right? The meaning in that stage play for this machine was forced labor. So the Czech meaning of the word robot is forced labor. So I think even today it is very applicable, very correct to say robot is basically forced labor. Then there's another affiliated word to robot, and that is robotics. Robotics is what? Uh, it is a science and engineering of using robots, right? Science and engineering of using robots. It's a field, right? Field. Um, it involves design, it involves applications, it involves research, etc. And that word first appeared in a science fiction um, titled Runaround by Isaac Asimov in 1938. So these are the little historical things, right? Uh, then let me portray robotics within our knowledge framework, right? We all know about various disciplines in engineering like mechanical, control, electrical, computer science, and then also classical fields like mathematics, right? We all know about these fields. So you put all these things together, you get robotics, something like that. So how we connect robotics to what we already know? Because in robotics, right, there's a lot of mechanical engineering. You have to study mechanics, how different parts of a robot move with respect to each other, and some parts are connected to other parts, right? They are not free. So you need to analyze static and dynamic situations, right? Static means it doesn't move, and there are forces, etc., applied on the system. The system is not moving, right? And sometimes the system moves, right? Like walking robot, right? Then you have to analyze dynamics, right? Speed and acceleration. Um, so all these things are actually mathematics, but they actually come under mechanical engineering. It's application of mathematics. Then mathematics is separately there, spatial motions and the attributes of manipulators, right? It's like using linear algebra, you can analyze a robot manipulator using matrices, transformations, a lot of things. Mathematics is an essential part in robotics. Then comes control theory, right? Because you need to control the manipulator, you need to read the sensors and think about what to do next, and then control actuators, and you control the robot, right? So control theory is a part in robotics. And you need to know about electrical and electronic engineering because there are a lot of sensors in robots and their power system in robots, right? Um, so how to interface these sensors and how to connect the power system, a lot of electrical and electronic engineering. And then comes computer science because you need to write down the code, the brain of the robot, right? This code will read the sensors and figure out what's happening in the environment, and then it knows what to do, and the code will have to decide how to actuate the actuators in order to perform the task. Okay, so if you combine all these things together, it's robotics. Now, because of this multidisciplinary nature of robotics, uh, nobody can say I'm an expert in robotics. So if you want to say I'm an expert in robotics, You need to be an expert in mechanical engineering, expert in mathematics, expert in control theory, expert in electrical engineering, expert in computer science. So it's hardly possible, right, for one person to be an expert in all these areas, right? So therefore, most of the advanced robotic stuff is implemented as groups. So in these groups, there are some people from mechanical side, some people from electrical side, some people from computer science, like that combined together. Because some you don't need to have a mathematician here, because this is not that kind of mathematics, pure mathematics, right? It's basically engineering mathematics, right? Linear algebra, etc. So therefore, you don't need a mathematician per se, right, in your robotics group. But make sure you have other experts, right, in the system, in your group rather. So that's why most of the robotics projects that we do here at Moratua, right, we do it in the final year, where you have 4 students. But most of the time, they are all electronic and telecommunication engineering. But you can always find out those people, they have the skills in computer science, right? And also mechanical engineering, SolidWorks, etc. They learn quite a lot. They are not experts in mechanical engineering, but to some extent, maybe half baked, right? But if they need some serious mechanical stuff, we always ask them to talk to their batchmates from mechanical department and get their expertise. Quite often we do that. Then only you can build a very good robot, right? So in your uh, workplaces, right, you might need to build a robotic system for certain applications, right? In that case also, please remember this diagram, right? Whether you have the right expertise, right? Otherwise, in the way you will figure out, oh, my God, I need an electronic engineer to do this sensor fusion or sensor interfacing, and I need a mechanical engineer to do this analysis. You haven't done this analysis, right? Oh, I need a computer science guy to code it. So you will surprise in the way when you struggle, right? So therefore, upfront on the day one, you need to form your team, right? Build your team. You have to bring in uh, all the necessary skills to the team before you start your robotics projects. Now, one fundamental idea of robotics is that in robotics, our desire is to synthesize some aspect of human function. Most of the time, it is like that, right? You can see robotic gadgets in the industry, but always if you look hard, you can figure out what is hidden deep inside is some sort of human function, okay? And you want to implement it using what? Mechanisms, sensors, actuators, and computers. By combining all these things, you need to create or build some sort of human function. And if you look at the robotics, the landscape, it's not a homogeneous landscape, it is a partitioned landscape. So you can see these partitions like mechanical manipulation. There are a lot of robots, manipulators in industry, in automobile industry, electronic industry, chemical industry. There are a lot of manipulators handling objects, assembling, mating, etc., cutting, seaming, painting. And then you have locomotion, right? Autonomous vehicles, right? All-terrain vehicles, stuff like that. And then you have some soft robotics part, right? Where computer vision is the main thing, right? Machine learning, computer vision, language processing, that kind of thing, right? There you don't see actually physical robot. And some people call it soft robots. I don't agree with that one. There's nothing called soft robots, right? But there is flexible robots, and you can say soft robots, but still there's a mechanical manifestation, right? In that, some people just call piece of software as a robot. No, it's not. But if the whole world needs that word, let it be. But a lot of people, including myself, I don't believe that is a meaningful thing to say soft robots, right? Soft part, the software is only part of a robot. But if you take only the software, it's not a robot, my view. And the other part is machine learning AI. So these are happening, right, with or without robots. Machine learning is there, with or without robots. Computer vision is there. There are so many applications, right? But when you look at robotics, you can bring in computer vision, you can bring in machine learning, you can bring in almost anything. Eventually, you have to build something which has some sort of human function, right? And it is not only the human brain. If somebody build just the brain, can you call it a robot? It's the thinking process. I don't call it a robot. It's only thinking. It's only the software. But when you put it on a machine and then machine starts working, yes, I call it a robot. Right? I call it robot. So this is uh, the definition and how you want to define a robot and how you want to uh, exclude other machines, right? Um, from calling as robots. So it's always important to figure out what we identify as robots. Now, if you look at the early days of robotics, we see the records like 1940s, the small robot like a tortoise, right? The Grey Waters tortoise. He designed and built this robot with some light sensors. When you shine a light, the robot can move to that direction, or you can program it to go the other direction or hide in the shade. Okay, so autonomous behavior. So you can see very clearly, even though it's a very basic thing, it manifests some sort of human function, right? Some sort of human function. In 45, they developed these master slave teleoperators to handle radioactive material in a uh, uh, fully sealed uh, room, right? This operator, the human operator, handle this material from a distance, but he can see it, right? He can see it. Uh, then in 60s, General Electric, they developed what is called walking truck. You can see this truck like a big walking machine, and there's a person here, and he controls the arms and make it walk. And in 60s, you have handyman. Uh, it's an exoskeleton that a person can wear, right? And then when he controls his arms and fingers, there are actual sensors here to capture the motion, the finger positions, angles, etc. And then you can communicate that to a similar exoskeleton somewhere else. And that exoskeleton can perform the same movements, right? Motions of this person. So they built it as far back as 1960. And into 60s, in Russia particularly, they developed prosthetic arms for disabled people. So maybe your forearm, part of your leg, and it's an artificial gadget you connect to your amputated arm or leg, right? And then you control it. When it comes to controls, maybe very basic to advanced. Okay, sometimes you can control these things using your brain. You think and it moves. Sometimes using your muscle signals, right? So these inventions, robotic gadgets, were developed in very old days, like 60s. Then into 70s, we see some underwater robotics, right? Vehicles, submersible vehicles, uh, with underwater vision, etc., right? Deployed for underwater search and operations. And also in 70s, we can see space robots deployed on moon. Right? This is a lunar rover, very old one, one of the most, one of the first lunar rovers. And this particular one is lunar code by Russian Federation. And that one traveled on the moon about 11 kilometers in 11 months. So roughly about a kilometer every month, right? Um, and also it experiences time delay and stability problems because I think they control it from the ground, right? You send a command, say move forward, it moves 1 meter and stop there, and maybe they got some videos, photos, and then looking at that they start moving again, uh, because you cannot operate a long or huge control loop, right, spanning from here to the moon. So certainly there can be some stability problems. Now these are very fascinating things, as you can see, right? Prosthetic arms underwater and in space. However, none of these things were actually very commercialized robotics. They're not. They're not, except for this one. This is the the type of robots that are commercialized. These robots are the industrial manipulators that you see in automobile industry and all the other industries, right? Performing various tasks, and they add value to the products, and therefore uh, they help generate revenue profits for those companies, right? Now these robots generate profit. Okay, so this robot is Unimate, the world's first commercial robot. Unimate, or first industrial robot. It was developed by George Devol and Joe Engelberger. So George Devol was a inventor. He's not a highly educated person, but he knows how to put things together and build something. Whereas Joe Engelberger is a scientist. Okay, so they got together and built this robot. So therefore, Joe Engelberg is known as father of robotics for this work, and this manipulator um, uh, is performing very simple operation: pick and place. Okay, pick and place. Now, if you look at the robotics landscape today to identify what are the different types of robots, this is what you see. You can see robots in space, teleoperation, telerobotics. Then you see medical robotics, robots in the operating theaters, etc., endoscopy, uh, and heart surgeries without opening the body. A lot of robotic stuff, right? Then you see flying robots, space robots, climbing robots. Then you see millibot teams, polybots, reconfigurable robots. I'll show you some of these robots in the upcoming slides. And then you have all-terrain robots, robots that can handle solid ground, very unstructured environments, even water, mud, right? On different planets where there is no regular or structured environment, self-driving cars, very advanced stuff, and telepresence robots. You know what telepresence robots are? Telepresence robot is a robot um, that you can remotely log into and then operate it from remotely and get the feedback, vision, and audio, everything, right, from that robot to you, right? So you make your presence, right, almost anywhere in the world using this robot, right? Telepresence robots. Then we have humanoids, service and caregiving robots. In the future, you will see robots, robot waiters in restaurants, right, serving you food, uh, and receptionists, right, uh, greeting you, and robot guides guiding you in museums, etc., without people, right? And also in some shops, cashiers, like that. Then robotic prosthetic limbs for disabled people to grasp things, to attend to their regular daily work without asking help all the time from others, right? Uh, then exploration and mapping robots. You in the world, you can see sometimes places like very radioactive and it's very dangerous to be there. War zones, very cold, very hot areas where we can't send people. You can always deploy robots, right? Uh, then biomimetic robots like robot dogs, robot horses, robot cockroaches, robot snakes, robot birds. And this is another area. There are some crazy people trying to build an animal, right, artificially, a robot, and figure out how the actual system works, right? Um, if they are really smart, they can get the robot to perform very close or as close as the actual animal, right, in the nature. Uh, then the surveillance robots, demining robots, aerial robots like drones, for example. Drones are actually flying robots, right? And you can see surveillance robots or surveillance drones coming to the world, right? Replacing the human security guards, patrolling staff. You can have these patrolling vehicles, surveillance robots, surveillance drones to do the job, right? Regularly, every night from say 8 o'clock to 6 a.m. in the morning, you can program these devices to take a walk around the periphery, right? To see whether there are intruders, whether there are people who are not supposed to be there, right? Just the job done by the security people, right? You can have robots do that. And then industrial robots. This is the biggest part of all of these robots, right? Industrial robots. The robots that you see in industry doing cutting, welding, seaming, etc., right? In various industries like electronic industry, circuit board manufacturing, and also in automobile industry, doing various tasks, right? So coming back to this telerobotics thing and space robotics, this is a very niche area, right? You know, the communication satellites in 36,000 kilometers above the Earth in the geostationary orbit, right? Um, some of the companies send the satellites, right, to the orbit, and after about 10, 15 years, they move that into what is called the graveyard orbit. So after the useful life, the satellites go to the graveyard. And now there's a project uh, uh, to prolong the lifetime of these satellites, to prolong the life of these satellites. But how? We're going to send another robot, right, which will attach to these satellites and correct the orbital attitudes, and if necessary, refuel it, some ammonia and other gases, refuel, and keep it in the orbit and keep it going for another 5 years. So extending the life of communication satellites, right? So when we do that, we can extend the life of these satellites by 50%, by 50%. So which means you are making use of the same satellite for 50% more time. And by doing that, you cut down your cost by 50%. And also you're gonna reduce the space waste, okay? Space waste, because every satellite unused, right, is a waste in the space. We are actually polluting the space. Space is a very, very big area. Volume is not easy to pollute. But anyway, conceptually, uh, at least we want to keep it clean. So this is a very interesting area. So I'm actually part of this project. We are starting this year. Um, how to control these two robots together, the satellite and the other one, right? The mission expansion vehicle, MEV, they dock together and then do the controls and refueling and everything. This has to be fully autonomous because there's absolutely no provision for human intervention, because the whole thing is happening 36,000 kilometers above us. So we have to design a force position, fusion control techniques to make sure that the support vehicle, that is MEV, mission extension vehicle, is able to perform this refueling and attitude correction of the communication satellite and keep it there in the right orbit. So therefore, there are a lot of advanced stuff uh, in robotics. Now, so I'm going to show you the structure of a telerobotic platform, telerobotic system over the internet. This is how you program it. So here you have the robot manipulator and the controller, right? The controller provides the power and control signals to the robot manipulator. And it is connected to this computer over the internet. This is where the operator is. This is where the operator is, right? When the operator issues a command, it comes over the internet, right, to this computer, and this computer takes this command and it executes the trajectory planning and whatever necessary actions all internally, and then issue the control signals to the joints, and then take the feedback, and it operates a closed loop controller locally, because this loop has to be very fast, right? You cannot run a complete loop like that, right? You can't run a complete loop like that because it takes a lot of time. Time delay means phase loss. Phase loss means instability. So your robot can destabilize pretty soon. So therefore, what we do is we operate a control system over the internet between the two places, remote operator and the local controller. But this is a like supervisory level of control system. Only high level commands move in within this loop, but all the control actions are happening within this loop, which is a very fast real-time control loop. Clear? Right. So this is something we built many years ago between South Korea and Japan. So this part was Japan, the robot and the controller, and remote operator was in KAIST, South Korea. So we implemented this and operated for quite some time. It was operating perfectly, not a single accident or any fiasco. So this is basic architecture of any robotic system over the internet. So there you can see the two bullets. The remote user, which is the human operator here, issues only high-level commands for which low-level motion planning is carried out by the local controller. Okay, feedback loop is locally implemented. Therefore, there's no stability problem. Okay, the feedback loop is locally implemented. So therefore, whatever high-level commands you are sending from here to the local controller, you need to know beforehand, right, that this command can be implemented by the local controller. You don't send anything, right, that the local controller cannot implement. Understand? If the local controller cannot implement a command, if you issue something like that, accidentally even, the local controller just neglect it and communicate back, sorry, I cannot implement your command. Okay, it works like that. So long-range teleoperation is not continuous. So this long-range teleoperation is not a continuous thing, right? But a stepped control process due to time delay. So you don't have a continuous feedback loop like that. It's a stepped control process. Step means you send a command and wait for some time until you get the video feedback, right? What is the latest? Then if you are happy with that, you can issue the next command like that. So let me show you this little video which shows you space teleoperation, ground space teleoperation. You can see the human operator here. He operates this hand device. Then it goes to the space, right? Then you can see some movement here, right? Based on the command here. And then you get the vision feedback. Once you have the feedback, the operator issues the next command. Okay. So he does not issue the commands continuously, but he issues the commands one at a time, and he gives enough time in between consecutive commands, okay, to make sure everything is happening properly. And here in this screen, you can see the simulated environment. This is the simulated environment. It gives the immediate feedback to the user what's going to happen, right, after issuing the command. So if there's any serious problem, he will know it immediately because the simulator will simulate it. The simulator has to be physics simulator, very accurate simulator, right? And after a little while, he will see the actual thing happening in the space, right? So what you see here is the actual telerobotic platform we built many years ago between South Korea and Japan. This is the South Korean side, and this is the Japan side, local controller and the remote supervisor. There you can see the vision feedback of this robot, right? The feedback comes from Japan to Korea, and looking at the vision feedback, uh, you can issue the commands using the arrow keys, right? Up, down, left, right, etc. So the control system happens in Linux system, Red Hat here, and the vision system happens in on Windows system. So you have two different systems, Windows and Linux, okay, Red Hat, for vision and controls. Now, let's say you want to design and build a teleoperated device, right? And you have the human at a distance, right? So this is a complicated system. How do you design the whole system? So I will use this one as an example. Let's say This is a golf playing robot. You can see the small golf table here, the hole in the middle, golf ball, and the putter, and the manipulator. So what you want to do remotely is that using the keyboard commands, right? Uh, Control the robot and push the ball into the hole. That's what you want to do. So if I give you this as an assignment and ask you to design the system, right? I expect this one. So this is the task at hand, to design a golf playing robot telerobot system. And I assign you to design the whole system, right? What I expect is something like this. So what is it? So these boxes, right? You identify your control actions. You need to control the position X, Y, Z, right? You need to control this position X, Y, Z. Say X, Y, and Z. Z is the depth. You want to control that. You need to figure out what you want to control. Number two, orientation control. You want to control the orientation. What is that? If you look at this pattern, it has to always face to the hole, right? This way, not this way or that way. You can move the putter wherever you want, but whenever you move the robot like that, the putter should face the hole always, right? Otherwise, you can't hit the ball to the hole. What else? Collision avoidance. You need to make sure this robot does not collide with anything, doesn't collide with the ground, doesn't collide with its own pieces. You see, if you turn this joint too much, it will collide on itself, right? You should avoid that happening. What else? Depth perception. The user need to know the depth, right? The depth. That is how high the putter is from the ground. Okay. Otherwise, without knowing, you can lower this until it hits. Eventually, it hits on the ground. A disaster, right? So, likewise, what I'm telling you is that you need to first write down these actions, the required actions. Then you need to figure out which of these actions are to be assigned to the remote user and which of these actions are to be assigned to the local controller. Because you know there's a local controller, right? Here, this local controller can perform certain tasks without human intervention. In fact, you need to assign the local controller to do as much as possible. Okay? Because it's a machine. It doesn't get tired. You can assign it to do anything, right? Which is possible, right? So you want to make sure you do not assign the remote operator too many things, because you can easily overload the remote operator if you assign too many things. So what I would do is that position control, I have to assign it to the remote user, because part of this project is actually to get the remote operator to do the job, not to automate the golf playing. Because if you want to automate golf playing, you don't need a remote operator anyway, right? You can program the robot through that. So therefore, position control is up to the remote user, even though you can completely control it within the robot local controller, right? So this is to be assigned to the remote user. Orientation control, right? That is too much for the remote user, because remote user cannot actually see properly the orientation, right? So I would assign it to the local control to control the orientation. So when the remote user controls the position wherever, right, within this area, Local controller can control the orientation of the putter accordingly, right? So that is the plan. Collision avoidance, completely local controller, because remote operator cannot see whether this is going to collide, right? Whether this putter is going to hit the ground. User cannot understand that because this is a two-dimensional weave, right? So therefore, I assign that to the local controller. Depth perception. Depth perception is a perception kind of thing. I assign it to the remote user, but I will facilitate it using a laser pointer. So there's a laser pointer here. You can see the dot on the ground is the laser pointer. It's always on. So the operator knows the position of the putter above the ground. So it should be somewhere over here. Okay, exactly at this point. Probably this is this point. This is the putter position. So the remote user can understand this. He can see the laser pointer so that he can move the robot this way, this way, this way, and a little bit further until he see the laser pointer over here. When this laser pointer comes over here, he knows he is in the right position to putt. Understand? So this laser pointer, laser dot on the ground is extremely important for the remote operator to understand the position, three-dimensional position of the manipulator. So likewise, this is an example. If you design a telerobotic platform, you need to understand these control actions and then figure out how to assign these actions to the remote user or the local controller. Okay, right. the the next category is polybots. So what is polybots? By the way, if you have any questions about telerobotics, space teleoperation and things like that, please ask before I move on to the other category. Any generic questions? Doesn't have to be technical or anything, out of curiosity. Because in the future, you will see a lot of robotic stuff over the internet, even telesurgery, people and patients being
Excuse sir,
operated.
can you hear me?
Yeah, go ahead.
Excuse sir.
Yes,
Hello.
go ahead. Go ahead, I can hear you.
So for the telerobot in
Yeah,
the say in the space, we are not for the telerobots.
yeah,
For the gravitational forces, how it's considered
yeah,
while
that's right.
planning the robot.
Yeah, so that's why I said you need to have a very good physics simulator to simulate, because in a simulator you can control your gravity also, right? Uh, Simulate your control algorithms, right? What sort of torques and forces are to be applied there, not the force and torques that you apply on the ground here, right? 36,000 kilometers away gravity is not as strong as here. So you know what is the gravitational field force is, intensity is, and then you can put that into your physics simulator, right? And figure it out. So when you do that, if the physics simulator is really a good one, most probably what you see on screen here would be the same thing that would happen on orbit when you implement it there. So that's how it happens. Your modeling, your simulation, you have to do it with that uh, gravitational field strength, not 9.8. Okay. Is that okay?
Yes, sir.
Any other questions, please? All right. So let me move on to the next one, polybots. So this is another area in robotics where uh, some researchers try to build modular robots. They call it modular reconfigurable robots. So there you can see three different robots. One is uh, like a wheel rolling on the ground to locomote, right? And there you can see like snake kind of robot, right? Locomotion is basically snake locomotion. And then here you can see a spider like platform. It can walk actually, okay? All these three types are built using same modules. You can see the modules here. So many modules together. You can connect them like a snake or like a wheel or like a spider. Okay. So you change the configuration using the same modules. So that is why it is called modular reconfigurable robots. So the research is how to build this module, because this module needs to have the degrees of freedom, the actuators, the sensors, power, everything built in, and it should be identical, right? You can't have different modules. They should be identical so that you can fit in these modules any uh, uh, any useful way. Okay. So let me show you. Oops. Okay, so you saw that I think it explained the whole thing about modular reconfigurable robot, right? So couple of highlights in that video. You saw the movement of the cubes is basically using a spinning mass inside the cube, right? I don't know whether the axis is rotatable or three axis or whatever, but if they get three axis spinning mass, they can move anywhere, any direction, okay? And then the magnetic structure, the spinning rotating magnets will help the cubes to stay together, right, and form a big structure. The third one, the researcher explained about the remote controls, right, sending through Wi-Fi to individual modules to what to do, how to do, etc. But in the future, he said it's all will be within the group. Let's say if it is a 10, 15 cubes, they will communicate each other. They will plan how to move as a group. So pretty amazing thing, right? If they actually do that. I don't think they have done it yet. Then eventually what you expect to see is a bunch of these cubes, right, stay together, form different shapes, and move and deploy themselves into a certain task. Okay, so it will be very, very interesting to see. Any questions about that, please? Modular reconfigurable robots. No questions? Okay, so then let's move on to the next one. Minimum invasive surgeries, medical robotics, right? So there I want to pick up what is called Da Vinci, right? Da Vinci is a telesurgery robot system. So what is a telesurgery robot system? So this illustration shows you what it is, right? You have the operating theater here. There's a patient. This is the bed, operating theater bed, and you have these tools here, right? You have these tools here. These surgical tools are operated by a remote surgeon, right? He can see what is happening over here through this high definition video, and he controls his hand devices here, right? Uh, which will control the actual surgical tools here in the theater, right? So these things are actually happening right now, right, for certain surgeries like endoscopy. You don't have to open the body of the patient, but you can insert these very small tools, uh, right? Very small surgical tools like where, like these ones, right? Through the body of the human. You don't have to cut the body, but make a small hole, incision in the body, like a small injury or something. Then you insert the tool into the body. So if the surgery goes well, you take the tools out, you don't have any permanent scar in your body. There's no permanent scar in your body after the surgery. The small 3 incisions will heal in few days. Okay. So you can immediately see the benefit. Sometimes when people undergo surgeries inside the body, the actual problem which is inside the body, right, um, uh, gets healed. There's no problem. But on the surface of the body, there's a big scar, maybe few inches at least, a cut. Sometimes that gets infected. Then you run into other problems. Okay, you went to the hospital to get operated on something which is inside your body, maybe your stomach, maybe your lungs or whatever, kidneys. Now it is okay, kidney is okay, the lung is okay, but you come home, after about a week, you have this additional infection on the body that you didn't have before the surgery. Okay, now you have to struggle with that problem. So the minimum invasive surgery, the name minimum invasive is because of that reason. We do not do any unnecessary damage to the body using a telesurgery technique, right? You do very little negligible intervention into the body, right? The surface of the body, the skin and all, to do the surgery. So let me show you this video, right? Da Vinci system. Do you hear the sounds?
No, sir.
You don't, right? So let me share the screen with the sounds. I think earlier you didn't hear anything, right? Anyway. Right.
The Da Vinci SI surgical system is the most advanced platform for minimally invasive surgery available in the world today. The integration of high-definition 3D vision, wristed instrumentation, and intuitive motion control enable the Da Vinci surgeon to transcend the limitations of conventional surgical technologies for a minimally invasive approach.
So these are the different surgical tools, right? These staff who are helping the surgeon is over here, right? For a demonstration, I think. Actually, the surgeon can be anywhere, right? Depending on the surgery, they have to use these tools, right?
Approach to a broad range of complex surgical procedures. 3 integrated components compose the Da Vinci SI surgical system.
This is the operator's console. You can see these gadgets here, left hand and the right hand. Okay, the surgeon has to learn how to use this technique. He has developed the skill to use these hand tools.
An ergonomic surgeon console. A patient.
Here you can see very clear view of the tool rack, right? There are different types of tools, but they are all like very small needles kind of thing, right? These are the small holes that you use these tools through the small holes in the body so that there's no big cut. There's no doctor to see what is inside the body, right? Everything happens to this. I think this is the camera system, right? You get the video camera through this one, right? These are the tools.
Side cart with 4 interactive robotic arms and a video tower housing the dedicated system processors and the high-definition 3D vision system. The Da Vinci system has been designed as a platform to deliver 3 key values: enhanced clinical capability for improved patient outcomes, streamlined design for ease of use that benefits the entire OR team, and extensibility for seamless OR integration. The system expands the possibilities for complex surgery performed with a minimally invasive approach. Clinical capability is enhanced in several important ways. The Da Vinci surgeon experiences a perfect alignment between his visual and motor axis, combining the familiar orientation of open surgery with the superior ergonomics provided by the console. Fingertip control of masters at the console translate the surgeon's hand movements to the robotic arms of the patient cart.
Now you see, this is a very unique design for a hand device, right? The surgeon uses his fingers like that, and his movements are captured, and then translate those movements to the tools, right, on the tool rack.
Motions are scaled to micro movements, and hand tremor is filtered out.
You hear that one, right? The movements of the surgeon, big movements, are scaled down when you operate the tools. So tools are moved, right? Small amounts. Like if you turn this, say, by 30-40 degrees, actual tool goes like maybe 5-6 degrees, right? So like that. So therefore, the operator feels like he gets a safe feeling. He knows that his movements are actually scaled down, right? The second one is, some people, they have hand tremors. The fingers are not very stable, right? There are tremors, right? You can remove the tremors through the system. That's an added advantage. Whereas if you get a doctor to do the operation, right, without this kind of system, whatever tremors in his hands will affect the operation as it is, okay? But now you can eliminate those tremors by filtering out and give a very clean motion command to the tool.
And hand tremor is filtered out. The Da Vinci Vision system displays high-definition video in two separate optical channels.
This is an actual operation coming from the video in one of the tools in the rack, okay?
For a true perception of depth during surgery. The immersive quality of the 3D visualization, combined with intuitive motion control, enables a virtual extension of the surgeon's hands and eyes into the operative field. Digital zoom allows highly magnified viewing of tissue without crowding the endoscope into the operative space. Increased surgeon confidence results from this superior view of tissue planes and the critical anatomy. The Da Vinci Si introduces higher resolution video into the console viewer for a new level of visual acuity greater than anything previously available. As the surgeon operates at the console, his controlling motions are
This is just a training session.
Translated by the system to the endowrist instruments. The Da Vinci system provides motion scaling that enables the surgeon to tailor the ratio of his hand movements to a corresponding micro movement at the instrument tip. Da Vinci EndoWrist instruments are designed with a unique wristed architecture, providing 7 degrees of freedom, a range of motion greater than even the human wrist. The system enables the surgeon to perform dexterous and very deliberate motion control of the instruments for precise dissection and reconstructive surgical tasks. The system requires that every surgical maneuver is under the direct control of the surgeon. Redundant safety checks prevent autonomous movement of the instruments or the robotic arms. Unlike conventional laparoscopic surgery, the robotic arms move around a fixed pivot point to...
This is a very interesting point. This is the point where the tool is inserted to the body. Now, when you move the tool, right, you should not move this point. This should be an invariant point, If you change this position, you're doing damage to the body, right? Already inserted. Now you can't move the tool around this point. But here you can make any movement. That's okay, rotate it, but not here. So this is something that the doctor cannot do, right? So, but you can program the invariant points of all the tools into the control tower of the system, so that the tower, that computer knows what are the invariant points, and it will keep the invariant point invariant without letting any movement of these points. Okay.
Reduced port site trauma for improved cosmesis and increased overall precision. During surgery, the internal view of the operative field is viewable by the entire OR team on the large vision card monitor. The monitor's widescreen view also allows the patient-side surgical assistant a broader perspective of the operative field, enabling better visualization of the procedure. Notations drawn on the external monitor are viewable by the surgeon at the console, enhancing communication for collaborative work and proctoring. The Da Vinci Si surgical system now supports dual console surgery. During surgery, each surgeon sees the same high-definition image of the anatomy from the 3D endoscope. Instrument control can be exchanged on the fly, allowing the first surgeon to hand over operative control of the instruments to the second surgeon, enabling a see and repeat model of instruction to be conducted during actual surgery. The dual console feature also allows two surgeons to operate in concert, with the first providing active, robotically enabled assistance on one arm, while the second surgeon uses the two primary instruments. This technical innovation is a first in robotic-assisted, minimally invasive surgery. It's designed to accelerate the learning curve and enable collaborative surgery in a precise, minimally invasive environment. With the Da Vinci Si system, the entire operative experience has been streamlined from setup to shutdown. At the surgeon console, a newly refined interface enables quick and clear system control and energy application. An interactive touchpad at the surgeon console provides comprehensive control of system settings. At the start of the procedure, the surgeon logs in and selects his desired video, audio, scaling, and ergonomics settings, which are retained by the Da Vinci Si system for future cases. Upon each successive login, the surgeon's preferences are automatically returned for an expedient setup. Adjustment of the system settings may also be performed with the intuitive interface of the vision cart. The simple touch panel interface enables OR staff to accelerate setup and intraoperative adjustments. The 3D HD vision system setup and controls have also been streamlined. Simple controls at the illuminator and 3D HD camera head enable quick vision system setup. The user-friendly design of EndoWrist instruments make intraoperative instrument exchange simple. LEDs that indicate status on each robotic arm provide feedback to the OR team on system status. The Da Vinci Si system offers superior digital OR integration. Patient monitoring and imaging modalities can be fed into the surgeon console view for information integration. This Tile Pro display is completely interactive and can be toggled between a view of the surgical field, display of patient-critical information, or multiple feeds in a tiled window. Integration with third-party devices, such as electrosurgical units, is now available for a wide array of energy instruments directly controllable at the surgeon console. The future of surgery includes enhanced visualization, superior instrument dexterity, and operative efficiency in a tightly integrated system. The Da Vinci Si HD system moves surgery forward with a new level of surgical capability that enables minimally invasive surgery in complex procedures as never before. Da Vinci provides a streamlined surgical experience that benefits the hospital, the surgeon, the OR team, and most importantly, the patient.
Right. Any questions about minimum invasive surgeries? This technology transforms the medical field into a totally new paradigm, and Now you can see increasingly many patients want to get operated through this system because it's only getting better, right? But for very critical surgeries like where you want to do open heart or brain surgeries, still the medical authorities, they do not allow this kind of systems, right? Because you need to have the human touch, human vision, uh, uh, in order to perform that kind of very risky surgeries, right? So the telesurgery, the minimum invasive surgery using systems like Da Vinci is for, I would say, relatively simple or moderately simple operations, routine operations, right? Okay, then. So let's get a little break here, yeah, about 10 minutes, and then we'll resume from here. All right. Let's move on to the next category. That is micro manipulation. Micro manipulation. So what is that? You know, in fields like biotechnology, right, or genetic engineering, right, we need to see and access and sometimes manipulate the very small world, the world of cells, viruses, genes, etc. Right? It is a few orders of magnitude smaller than our world. So we operate not in centimeter, millimeter scale, but maybe micrometer scale. So obviously we can't do it in this world. We need to have a robotic system. In a way, it's like teleoperation again. To scale down all the movements and scale up the vision, right? From the reality to our world, that is the vision, and from our world to the reality to the smaller world, that is the controls. Okay. So in these areas, biotechnology, microsurgery, microassembly, microchips, right? You need this kind of technology, and in robotics landscape, we call it micro manipulation. So let's see whether, but I don't think it's working this particular video. So I asked you to go to the internet and look at micro manipulation, right? Or else let me pull it from the videos. You can see it over here, micro manipulation. Where is that? Here.
Micromanipulation has many exciting areas and applications. Microtelemanipulator makes remote handling of microscopic objects possible. The micromanipulator has sub-micrometer resolution. The micromanipulator is shown.
So see here, the movement of the human hand is scaled down few orders of magnitude to sub-micrometer scale, and you see it's being operated in that small world. But the person doesn't actually see this scaling down or scaling up. That's the beauty of the system. What he sees is what he sees on the screen. He doesn't see the real world. He sees the scale up version, and all the movements are scaled down. So the scaling up the vision and scaling down the controls, right, conceal the scale of the two worlds. So the user sees that he operates in the same world, our world. And if you are in the micro world, you see there's somebody in the micro world operating the thing in that same scale. Okay. So that's how it happens.
To separate glass balls having diameter of 30 micrometers.
All right. Any questions about that micro manipulation? Okay. Now let's move on to the service and caregiving robots. This area is basically for welfare of disabled people. There are a lot of people disabled, and for their entire lives, they don't have some human function. Okay. Some people cannot eat themselves, and there should be a feeding robot. Here, what you see is a feeding robot, right? If not for this robot, these people, they have to ask other people, could you please help me for lunch, breakfast, for dinner? And they have to do it day in and day out. So every time they want to have a meal and they can't do it themselves, they're mentally down. Okay. They're mentally sick, worried people. Every day they're worried, right? So this is not just a technology that you see elsewhere. This technology will make these people at least able to help themselves for their meals, okay, without asking others help. So they feel like independent. They can attend to their own work, right? They don't depend on other people very much. That will help them to maintain a healthy mentality, right? So mental health is very important for disabled people, because very easily these people who are physically disabled can be mentally sick as well, right? So that is why this technology is extremely important.
Det er en spiserobot. Den er tiltænkt folk, der ikke kan spise selv, som eventuelt har mistet brugen af, eller mistet evnen til at bruge hænderne, eller på andre måder ikke kan spise selv og skal have hjælp til det. Men hvis vi nu antager, at jeg er en person, der skal styre joysticket med hagen, så gør jeg lige.
So this is how
Yeah,
the robot is activated using the chin.
Mens min læbe den rører ved pinden, så holder den stille, og så fjerner skaffen, så den rykker sig tilbage, så jeg kan få fat i maden. Når jeg så flytter mit hoved, så kan den mærke, at nu er der ikke mere aktivitet på skeen, så nu kører den tilbage i udgangspositionen. Og sådan bliver man ved, indtil man er midt.
Ja, man har tømt en slikpose.
Ja, eller slikposen er tømt, ja.
Yes. So you saw it, right? So what's your comment? It's a simple robot, right? It's not that expensive. It doesn't look so. And it's not very intelligent. There should be a lunch box which is very well structured, and there should be small items, and not like the normal lunch pack that we have in Sri Lanka, and there's no way to take different pieces of different dishes and then mix up together. It's not the normal lunch, right? That normal people without any disability used to have, right? This is a pretty much structured meal, right? And the robot is designed to pick up whatever from the compartment, right? And then you can easily improve this kind of robot. Say, for example, the 4 compartments in the box, you can have 4 different types of items. Then the robot goes in the rotation 1, 2, 3, 4, like that, right? To make the meal a bit more entertaining. So likewise, and also you can add the latest vision technology machine learning or whatever to make it more effective, right? Any comments on this, please? So be informed that this lecture is not for talking, right? In the final exam, I will definitely ask some of this information, right? So you need to be very versatile on all of these things, right? You should be able to critically assess these technologies, right? There are pluses and minuses, why they are important, and room for development. Everything I speak to you, right, you need to be very knowledgeable about, right? And in the paper, you will be tested for your knowledge on these different robotic platforms. Then actuation by muscle signals, EMG. So this also falls into the welfare robotics field, where we design and develop robotic gadgets to help disabled people, right? For people who have lost their upper limbs, right, and amputated arms and all, there are prosthetic limbs. But the problem is, how do you control the prosthetic limbs? Let's say the person wants to have some water, right? And he has to grab the glass of water using the robotic arm, using his fingers and all, right? So to control the fingers, you need to generate the muscle signals. The muscle signals are coming from, actually the signals are coming from the brain, the nervous system, and then onto the muscles like that. You can see it over here, right? So the problem is the signals do not go from here to the fingers because there is no arm. Let's say the forearm is amputated. There's no forearm. It's a robotic arm. So what you want to do is to connect these signals that have come all the way from the brain to this point, okay, and connect those signals to the prosthetic limb and operate the prosthetic limb. Right? In order to do that, you have to extract these signals. So here you can see some EMG signals. We call it EMG, electromyogram signals. Those are the signals coming from the muscles, the activities of the muscles. So it looks like a very noisy signal, right? So, but there is some information encoded in this signal. So if you can read what is that signal encoded, you can use those signals to control the prosthetic limb. So that is how it works. Here in this video, you can see a boy who has an amputated arm, and it is being fitted with a robotic arm, and he has gone through a rigorous training process how to connect the muscle signals to the hand and actually use the hand somewhat similar to the actual hand. Okay. can perform some strange movements also. Right? Normal people can't do that.
Peter, could you close the hand?
So this is actually the training process, because these robotic gadgets are very generic gadgets. They are actually, you can have these prosthetic limbs customized build to a particular person. But more often what we see is a generic arm with a generic training platform. So once you have a generic thing, it's like free a fit kind of thing, an outfit which is free, right? Then you have to take it and fit on to you, right? So likewise, this arm also to be trained to a particular person. So for that, they have to undergo this process.
Great, and then open it. Could you pronate, could you rotate the hand and in the other direction? So Patrick, could you close the hand? And now open it. Could you flex it? And then extend.
See that? So after going through this process, the control gains, remember the PID gains? I don't know whether it is actually PID or something else. I hope it is some sort of PID. In the process, the gains are tuned automatically, right? Now this is one thing. The other one in the same category is power assist. You may have heard that if you take a normal human being, right? A normal human being can lift, let's say, how much? Say 50 kilograms, right? Now, if you provide an exoskeleton with some power assist, right, you would be able to lift 100 kilograms easily, because you actually lift 50. The exoskeleton provides additional power for 50 more kilograms. So eventually it will be 100 kilograms. So these devices are already available.
Robot Suit HAL, or Hybrid Assistive Limb, allows its user to easily lift a 40-kilogram Duralumin case, like this. Now look what happens if an elderly person who has been bound to a wheelchair wears the suit.
She walked smoothly. It's amazing. I was surprised.
This hospital in Yamaguchi, Western Japan, has been leasing this robot suit for about $2,000 per month. The staff hope the suit will help patients remember what it feels like to walk, leading to faster rehabilitation. Hifumi Fukushima, who is 74 years old, suffered a stroke twice. With his lower body paralyzed, he has been unable to walk for the past 5 years. But look at what happens when he wears the robot suit.
When I go upstairs, I'm surprised I can lift my feet this way.
This is how HAL works. When a person tries to move his leg, electrical impulses flow from the brain to the leg muscles. The sensor detects the brain signals and sends commands to the motor. Then, the robot suit begins to assist the leg muscles. This occurs the instant the person thinks to move his legs. That's why the robot suit moves smoothly, as if it's part of the wearer's body. HAL was developed by Professor Yoshiyuki Sankai of the University of Tsukuba Graduate School. He is also the CEO of a venture firm called Cyberdyne. Sankai started to develop robot suits 20 years ago. First, he worked on the human brain's electrical signals to identify the impulses linking the brain to leg movement. Then, the professor spent 4 years finding the proper timing for conveying the electrical signals to the motor. And at last, 6 years ago, he completed a test model. But with a computer and a battery pack, the suit weighed 22 kilograms. It took 2 people to help put the suit on. It was far short of being practical. But Hal now weighs less than 10 kilograms, half that of the test model, and a compact battery pack and computer are neatly set around the waist. Hal comes in 3 sizes: small, medium, and large. This year, the venture firm began mass production of the suits. Inquiries have flooded in from hospitals and other care facilities, both in-country and abroad. It will make 500 units a year.
Up to now, robots had been simply the result of some academic research. But finally, they've begun to be useful in our daily lives.
Sankai is now developing a full-body model. He believes such devices will help reduce the burden for care workers. The suit will allow a wearer to easily carry a man weighing 60 kilograms. Sankai hopes to complete a marketable model next year.
Some care workers are forced to quit their jobs because of lower back pain, even though they desperately want to help those who need care. I want to provide technological support for such workers.
Robot suits have begun to be used in the fields of rehabilitation and nursing care.
Okay, you saw that the whole story, right, is much more than the technology, as you saw it, right? Some people have not been able to walk for their, say, last 5 years or so, and then with the exoskeleton power assist, lower limb power assist device, now they can stand up and walk. Now see how big of a transformation that for their lives, right, and their families and all. It's a huge thing that the technology can provide to humanity. And finally, you saw Professor Sankai is developing the full body model, right? Not only to stand up and walk, but this is for the workers who have to lift heavy stuff, and they are prone to back pains and disabilities, right, when they grow older. So the power assist devices will help them to reduce the back pains and huge amounts of strains on their body, right? So it's a very serious thing. And the other point I want to make here is that this power assist device, it takes the signal from the muscles, as you saw in the video. So when the muscles are actuated, like say as you walk, right, your thigh muscles are actuated, right, periodically. So this actuation is the signal that is used by the power assist unit also device. So therefore, if you do not want to walk, there is no power from the power assistive device. It is only when you try to walk that the assistance comes in. Okay, there's nobody controlling it. You control it yourself, right? If you want more power, the power assist delivers it when you need it, right? Not when you don't need it. Like if you saw some preliminary videos of this research, right, by Professor Sankai and his students in Tsukuba University in Japan. And at that time, the power assistive device provided power at a different time, not when the user needs it, because at that time the technology was not there. So therefore, the power assistive device, how it controls the power, and also the human being who needs power at some points were not in synchronization. They are asynchronous things. So therefore, what happened was, as you saw in that video, the person couldn't actually walk, because to walk you need to get power in a particular synchronized manner, the leg movement and the power coming from the assistive device. There should be some sort of synchronization, some sort of harmony. To get to that harmony was very difficult at the beginning, and to get the right amount of power is also very important. Okay, any questions about that? Okay, so let me move on to the next category. Still it is probably the same category, but slightly different type: actuation by brain signals. So the few assistive devices that you saw here, right, earlier, they take the signals from the muscles. So muscle signals, or EMG, are in microvolt range. Okay, or maybe not micro, maybe sub-millivolt range. So somewhat stronger, so that you can take it and refine it and amplify and use it. But if you really want to control a prosthetic limb using brain signals, right, this is yet another research, a harder part than using the muscle signals. You need to tap the signals from the brain. As you see over here, you need to have a head cap and electrodes, and then take the signals, amplify, condition, and then intention reading. You need to read the intention. So when the muscles are actuated, you know what is to be done. It is pretty clear. Okay, when the muscles are actuated, it's the leg movement. But if you look at the brain signal, how do you know, right, that these brain signals are actually related to muscle movement? Which muscle movement? So therefore, you need to do a lot of other research, how to correlate the brain signals with the muscle signals, right? So when you get the brain signals, you also have to get the muscle signals and try to figure out some sort of relationship, right? And then rather than tapping the signals from the muscles, you tap it from the brain, right? The difficulty is that if you tap the signals from the muscles, it's like sub-millivolt range. But if you tap the signals from the brain, it is microvolt range. Okay, so you are in deep trouble working with very, very weak signals. That is one thing. Second problem is, you do not know what the signals really mean, right? Intention reading. For that, you need to do a lot of research to find out, if you see signals like that, how to decode these signals into the intention, right? So there are a lot of difficulties here if you want to work with the brain signals. But the advantage, if you get everything right, is that using the brain signals, you can read the intention, a lot of things, not only the muscle activity, so many other things can be read from the brain signals, right? So there are advantages as well as difficulties or disadvantages. So here you can see the EEG signal, electroencephalogram, that's how we call it. You can see here so many electrodes placed on the head. This is the nose, left ear, right ear, right? And these are the channels from 1 to 16. This is a 16 channel head cap, and you can see the brain signals changing. You can still see some activity over here, here, and here, right? And if you see it from here, there you can see after collecting a lot of EEG signals from different people and giving it to a meaning, right? Today, this area has developed to a certain level that they can actually read some of the basic signals. Like, for example, if you see a brain signal like this, we call it theta wave. And if you see it something like this, it's a delta wave. If you see something like this, it's alpha. And if you see something like this, is beta. There's no kappa, omega, and other things. No, nothing. Only these four: theta, delta, alpha, and beta. Okay. But you don't know at what time you get theta, at what time you get delta. And if you have 16 channels like that, you don't know when channel 1 gets alpha, whether channel 2 gets beta, or whether channel 3 gets alpha or theta, whatever. All these 16 channels at any time can get you any one of these four. So now mathematically it's a bit easy thing for modeling at least. And then if you look at all these 16 channels and the combination of how many thetas, betas versus alphas, etc., you can get into the intention of the person, whether the person wants to do what. Okay, so that's how it works. Any questions about that? Working with brain signals and try to get brain signals to design and build prosthetic limbs or maybe any other robotic gadgets. Any questions on that? Okay, let's move on to robotic grasping. So this is another area, how to build robotic gadgets, maybe humanoid robots, to grasp objects. This is one of the research we did many years ago. We use a force sensor, actually two of them, and captured the force signal as we grasp it. And this is what we saw, right? This is what we saw. The actual graph is in red, how the force is applied when you grab it and lift it. This is a 7 ampere hour battery. But what we figured out was it's very simple. First order rise, the best fit, right? So which means you can have this first order rise graph to apply forces to your robotic hand. So it will behave like human grasping. So you can design and build robots that are similar to humans this way. You first ask a human being to perform a certain activity. In this case, it is grasping, and you capture everything what you want. And then you implement the same thing on a robot, right? The robot will work, perform similar to the human, right? So that is how the this part of the robotics field works and develops. There are many robotic hands, grasping devices in the world, right? You can see a lot of things. I request you to go to the internet and see some of these things. DLR robots, right? Very fantastic company designing and building very interesting stuff like grasping. And here you can see two finger hand, right? Just two fingers. But look at the design, right? This design lets the two finger arm hand to grasp various different types of objects like the discs, cylinders, the cubes, right? Grasping from outside and inside, so many different ways, right? So let's see some of these videos. And this one is an adaptive gripper, right? It adapts to the object. See, very strong grip, right? Look at the finger design. So it adapts to the shape of the object. Okay, so let me show you the other one, suction gripper. This is pancake industry, right? This gripper is a suction gripper. It's not a finger gripper, adaptive gripper, right? This is designed for a particular application. So it's not a generic design, just for this particular application. So there's a vision system. When the pancakes come on the conveyor, they come in different positions, right? Irregularly placed. The vision system looks at it and figured out the locations of the pancakes on the conveyor belt, right? And then immediately communicate it to the robot arm so that it moves and picks it up. So finally, what comes out is a stack of pancakes, 4 pancakes, right? So see, can make industries very efficient, profitable if you use the technology, right? Now, there are very interesting other areas in robotics, like biomimetic robots. Some researchers try to design and build robots to mimic different animals, right? So you can see cheetah and snake, cheetah and snake. This is cheetah. see the speed, 25 or 26 miles per hour. So this is Boston Dynamics, another company in US. They are very reputed for various number of unique robot designs, right? And in this particular case, there is this boom that you can see over here to hold the robot on the belt. But this one is not doing anything else rather than just helping it to stay there. Entire running is by the 4 legs, right? So that is probably the fastest robot in the world. It's not a complete robot though, right? Then look at the snake. This is from Japan, ACM R5 from Tokyo Tech. Now this one is in a way a modular robot that I explained you earlier. Identical units you can see, right? Identical units, they communicate each other and they control individually, but according to a common plan, right? So every unit knows how their individual movements are movements contribute to the whole movement of the robot, right? And when you fit the modules together from the head to the tail, they know how many modules are there, and then they can coordinate the movement. And in water, it is even more fascinating. Because in water, you get the reflected force, right, easily. This is another very interesting area in basically mathematics, not in robotics, because you need to develop mathematical models, right, for this locomotion. If you do a particular movement of one of these modules in water, what is the kind of reflected force you get from water, and how you can combine these reflected forces of all the units to generate a profile, motion profile for the robot, right? It's a complicated modeling exercise. Okay. Then expressive robotic creatures. So what are they? This is very old research done again at MIT US to build a robotic creature that is able to express different emotions, right? For example, surprise, anger, calm, disgust, happiness, interest, sadness, etc., right? So by combining different features in the face, right, they try to combine these individual features of the face to communicate these emotions. Then into the humanoids and legged robots, right? The most famous humanoid one is, of course, Asimo, Honda Asimo, right? So let me show you Honda Asimo. I think everybody has seen it. this is Asimo. It has the sensors to detect obstacles and then to avoid obstacles, right? So this is voice recognition.
お飲み物をお伺いします。
オレンジジュースをお願いします。
井上さん、ミルクティーですね。岩下さん、オレンジジュースですね。西名さん、ホットコーヒーですね。それでは、持ってまいりますので。
So in this case, three people, they are asking some drinks from the robot, right? At the same time. So if I play this one again, you can see that.
お飲み物をお伺いします。
オレンジジュースをお願いします。
Now see all these, now these three ladies, they are asking, one is probably orange, the other one is tea, and the other one is coffee or something. The robot actually listen to the three requests at the same time and then figures out from which direction the coffee is coming, from which direction the other ones are coming, orange and tea or whatever. And it figures out very accurately, right?
井上さん、ミルクティーですね。岩下さん、オレンジジュースですね。西名さん、ホットコーヒーですね。それでは、持ってまいりますので、少々お待ちください。いらっしゃいませ。岩下さん、ご案内いたします。いらっしゃいませ。お待ちしておりました。ご案内いたします。岩下さん、どうぞこちらへおかけください。お飲み物をご用意しております。岩下さん、ASIMOは、ホンダの社会活動について紹介しています。お待ちの間、聞いていただけませんか？
はい。
はい。それでは、あちらのディスプレイを使ってお話しします。それでは、ホンダの地球環境への取り組み、ビーチクリーン活動についてリポートしてきましたのでご紹介します。岩下さん、こちらをご覧ください。ビーチクリーン活動を担当する社会活動推進室大野さんにインタビューしてきました。それでは再生しますね。
このマシンはホンダの ATV に独自開発した軽量でコンパクトな機材を装着し、
岩下さん、ご注文のお飲み物が来ました。こちらに置きますね。
You can see over here, when you design the robotic systems, you need to restructure the environment also, right? Otherwise, it will be extremely difficult to make a robot which is able to work exactly as a human would do, right? So therefore, when ASIMO picks up the drinks, right, it should be properly presented to the robot to pick up easily. And also when the robot wants to leave it on the table, you can see the mark here. The vision system of the robot looks at the mark and try to place the drinks on that mark. So likewise, using simple symbols, um, uh, mm, so the vision system can detect and understand, you need to use those symbols, right? To make it make life easy for the robot.
ありがとう。
Right. So let me show you the big dog. This is another. This is a very complicated robot designed and built by, again, Boston Dynamics. This is a.
Your screen is not shared.
Oh, really? Oh. Maybe I was disconnected, right? Right. Okay. Can you see the screen now?
Yes, sir.
Right. So let me show you what is called Big Dog, right? Big Dog is a very famous robot by Boston Dynamics. Now see, Big Dog is not a recent robot. It's at least about 5 years old. Then they actually started building version 1, 2, 3 like that. This is probably one of the latest ones, where they put a neck and a head to the robot, right? Like over here. And then got the robot to actually grab this cement block. It's a big cement block, and then throw it. Okay. And while it is performing all this grabbing and throwing of this object, the robot has to keep the stability, right? So it's a complicated thing. So that is a fantastic thing to see, right? Okay. The next one is exploration and mapping robots. There are mines, abandoned mines, particularly in other parts of the world, not in Sri Lanka, probably in US and Europe, right? And these mines are very old. Sometimes there are poisonous gases inside. And when there are constructions going on in certain areas, where these mines are there underground and people don't know about it. You get some people get trapped in the mines, right? Or poisonous gases. Um, uh, it has caused a lot of problems. So therefore, not recently, but some time back, there were some projects in the US to have this groundhog uh, by Sebastian Thurn at Stanford and some other researchers to develop these robots to go into these tunnels, mines, and get the video feedback and other chemical sensors to see, to detect whether there are any poisonous gases, right? And the laser scanners to get the actual scan of uh, uh, the mines. And in the same time, I want to show you something, which is this one. Just look at this vehicle, right? Uh, and see the design. So you see that one. Now, 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 tell me, is that last one a robot? So, so I just want to know your views. The last one, last video that you saw, uh, what do you think is a robot? Oh, who says it's not a robot?
The cutting edges or the cutting points,
Yes.
not the vehicle as a whole, but the tool used to cut the grass or the things, because they adjust themselves according to the obstacle and do the cutting.
Right. Any other views? So Sandeep says not a robot. Any other views, please? You saw the robot, right? You can use it for multiple applications.
So it's not a robot because this machine operating in human.
Okay, it's entirely operated by a human, so it's not a robot. Right. Any other views? Any other explanations than what we already heard? Right. Actually, my judgment is also the same. I can't say it's a robot. The reasons are, one, as you guys said, is manually operated. It's a machine that is operated by a human, right? But it has some fantastic designs, right? To cut the tree branches, cut grass, wash whatever name boards on the road. Fantastic mechanical designs. Even the grass cutter, which goes around this post and all that, is a marvelous design, mechanical design. But it's not a robot. I don't think it senses the post and rotate it around that. No, it's actually automatic. When it goes into the groove, it automatically turns. The person doesn't have to do anything. He just had to drive forward, and as he drives forward, the whole thing rotates. It's a mechanical design, just a mechanical design. Okay, so it's guided by itself. So therefore, I don't think it's a robot. Next one is the planetary exploration robots. You have seen a couple of robots in the last couple of years landed on Mars, right, and then explore the planet and collect soil samples and test those soil samples and send back the results. What were the chemicals on the ground? And also got some very clear photographs of Mars on the surface. Couple of Mars missions, right? So these are all robotic stuff. So see, this is how the Curiosity rover landed on planet Mars.
So the voice is not clear. Or
Can you hear the voice?
the video voice we can't, sir.
Okay, hold on.
Hi, I'm Jessica Samuels, member of the Engineering Operations Team, and this is your Curiosity Rover Report. So since the nail-biting entry, descent, and landing event, we're happy to report that Curiosity is healthy and clicking off all the activities that we asked her to perform for the first few days on the surface. We first deployed the high-gain antenna to facilitate communications back to Earth so that we can communicate with Curiosity much more efficiently. We've deployed the remote sensing mast so we can start acquiring our beautiful panoramic images, and we've also checked out what the state of the rover is by looking at ourselves in addition to the Martian landscape. we were happy to find that we weren't covered in a large amount of dust as some members of the team thought might happen. In actuality, we just have some of these pebbles that have strewn the rover deck with just a fine, fine layer of dust, which is well within the operating limits of the rover. So coming up, we're going to give the rover a brain transplant.
Now, this robot is actually a geologist, okay? Geologist. And for your information, whenever NASA send rovers to other planets like Moon or Mars, most probably and almost always they are geologists, right? Robot geologist. All what they need to do is to get the soil samples into the labs inside the robot, test it and get us the data, right? So they are geologists. Sometimes they drill onto the rocks a few centimeters and they collect the material samples from the surface, the first centimeter, second centimeter, third centimeter, like that, and figure out is there any difference in the chemical composition, so that they can trace back the history of the planet millions of years back, right?
We're wiping away all of the cruise and entry, descent, and landing software and making room for the software needed to perform the exciting portions of the surface mission ahead. We're giving the rover the capability to do the sampling portion of the mission.
This is the robotic arm on the Mars rover,
as well as being able to drive more efficiently to different targets on the surface. While we're doing the software upgrade, we'll still be sending images from the entry, descent, and landing event, as well as different images from the panoramas that will give us a view of what the landscape looks like around the rover. So that's your Curiosity rover report. Please check in often for future.
All right. Now, we also have built a holonomic mobile platform. This one, many years ago at Moratour. You can see it over here. It's a 4-wheel platform, and steering can be done with another 4 wheels, right? 4 motors. So you have altogether 8 motors, 4 for driving, 4 for steering. So because of this structure, this robot can actually is a holonomic robot, right? So it can move any direction without changing its heading. So these vehicles are required for adaptive parking. So you can drive forward and then turn the wheel by 90 degrees and park laterally to the parking lot. You don't have to go back and forth, back and forth, back and forth like in motor vehicles, right? If you have this kind of platform, you straight drive and then park by 90 degrees, right? Straight away into the parking lot. So easy. And this is another all-terrain mobile platform called RX. So let's see that one also. So it can handle almost any terrain because of the mobile platform. You can see 6 legs, but the legs are rotary legs, right? And they're not wheels. They're not legs either. Is something in between. So it has advantages or capabilities of wheels, and in the same time the capabilities of legs. So can handle almost any terrain. Okay. This is mudslinging, and also in water you can change the legs into fins and then it can actually swim in the water, right? It's truly an all-terrain vehicle. This is how it swims. Can you see the screen, by the way?
No, sir.
Yeah, I got disconnected briefly. That's why. Okay, but I think I played the video to almost the full length. Right. So I want to stop at this point today with mobile platforms, and we'll continue from the avoidance of dynamic obstacles maybe next week, right? Yes. Any questions so far? Now, if I give you a very brief, what we did today is we try to look at different types of robots, right? It's very important to know these different areas in robotics and some of the basic features there, right? For your general knowledge to figure out what the landscape is in robotics. But after that, we're gonna spend time to study more into industrial manipulators for the most part of the semester. So that's what the lineup is. Okay, then that's it for the lecture today, and I'll see you next week. Have a good night.
Thank you, sir.
Thank you.
Thank you, sir.